Now, in studying exponential functions, it's important that we talk about the number e, which is called the natural number e. Of all possible choices of bases, the most preferred, or the most natural base, is the number e. The number e has important significance in science and mathematics, and is often called Eulers number. This is not pronounced Euler, like a ruler with an e. It's pronounced Euler, like the football team. Is named after Leonhard Euler. This number is approximated, this should be approximate, 2.7182818, so on and so forth. Kind of like pi, where it's an irrational number that keeps going on forever, never repeating. E is an irrational number. There's no repeats in e. The number e is defined by this function. If n is a positive integer, then if we take the expression 1 plus 1 over n raised to the n, and I let n get really, really, really big, that's what this means. N is approaching infinity. Well, we know it can't ever get actually to infinity because infinity is more of an idea or a concept, but if I plug in values really, really close to infinity, then this expression gets really, really, really close to e. So when I plug in 1 plus 1 over 1 is 2, and 2 to the 1 is 2. If I plug in 2, I get 1 plus 1 over 2, that's 1.5 raised to the 2 is going to be 2.25. If I keep going 1, 2, 3, it's going to take me a really long time to get big. Remember, we're trying to approach infinity, so we're going to start getting bigger here. If I take 1 plus 100th, that's 1 and 100th, raised to the 100th, I'm getting 2.70, and so on and so forth. Notice these numbers, as n gets really, really large, approaching infinity, these numbers are approaching this number 2.71828, which as n gets infinitely closer to infinity, this expression gets closer to this value e. I need you to know that e is a very, very, very important number. It says in science and mathematics and finance. It comes up in several different places, and so whatever your field you're going to be going into, there's a high likelihood that you may run into this number again. This may be the first time you're ever seeing e as a number, but please note that the number e is a number and not a variable. We've never used e as a variable in the past. I'm not sure if you've really even kind of noticed that. There's some letters we steer clear of. Instead of using x's or y's or z's as variables, we don't use e as a variable because e means something else, which is this natural number. Now, because it is the most preferred or natural base, it comes up a lot in exponential functions, so we're going to need to talk about that. So the first thing we're going to do is sketch f of x equals e to the x. And in order to find out what e to the x looks like, we're going to have to use a calculator. And we'll teach you how to plug some of these values in. I'm going to start with our three key points. E to the negative 1 is going to be 1 over e, but I really don't know what 1 over e is because e is a decimal approximation. So what we're going to do is I'm going to pull up the graphing calculator and show you how to type in e to the negative 1. The e button close to the ln button, e to the x. So what we're going to do is hit second, the ln button, which should pop up e caret. Notice it already says raised to the because it's often used as a base. So usually in the calculators it automatically does that for you. If you're using a scientific calculator, you might have to type in the caret yourself. But we have e to the negative 1, closing my parentheses, hit enter. That gets me 0.37. E to the 0, well, I could probably do that one in my head, but just in case you were wondering, e to the 0 does equal 1, which we thought it was going to equal 1 anyway. E to the 0, because e is a number, is 1. And e to the 1 is just the decimal approximation, but we're going to go ahead and practice this one more time. If I hit the second button, the ln button, positive 1, e to the 1 is equal to 2.71828. And your calculator has this e number programmed into it, so you don't ever have to memorize it. You can just always open up your calculator and use that. 2.72. Now this is probably enough, but we're going to go ahead and just use one more, just because we do have our calculators handy. I'm going to go ahead and try e to the 2, so I get a more accurate graph. That's going to be 7.39. My horizontal asymptote, notice I haven't done any vertical shifting, is going to be the same x-axis, or y equals 0. So let's see, I'm going to graph this in black. -1, 0.37, 0, 1, 1, 2.7, and 2, 7.39. Using my horizontal asymptote at y equals 0, I can graph a pretty good line. My red function is f of x equals e to the x minus 4. Notice we have the same parent function, e to the x. So because I have the same parent function, I'm going to use the same black function, and then I'm only going to minus 4 to the x means right 4 units. Because I did not shift up or down, my horizontal asymptote will stay the same. So I'm going to take the black function and move it right 1, 2, 3, 4. Each of those right 4. Keeping my horizontal asymptote y equals 0. I have this function, which looks like the black function shifted to the right 4. For my green function, f of x is equal to e to the x plus 3. Notice plus 3 is on the outside of the function, so we're adding 3 to the function, which means I'm going to be shifting up 3 units. Because I'm shifting up or down, a vertical shift, my horizontal asymptote is now shifted. The only time your horizontal asymptote shifts is if you're shifting up or down for exponential functions. So I'm going to take my horizontal asymptote, which is y equals 0, and shift it up 3 units to be y equals 3 for my green function. Each of my black parent function key points is going to shift up 1, 2, 3. 1, 2, off my graph a little bit. Okay, now I can connect my points using my new horizontal asymptote to sketch my exponential function. On my blue function, f of x equals e to the negative x, notice I still have the same parent function, e to the x. The only difference is I have a negative. A negative tells me that there's a reflection. On our last example, we had a negative in front of the function, which reflected over the x-axis. But in this case, I have a negative in front of the x, not the whole function, but only the x and the exponent, which tells me I'm a reflection again, but this time I'm reflecting over the y-axis. If I take my horizontal asymptote of my parent function y equals 0, which is the x-axis, and reflect it over the y-axis, well, the left side of the x-axis will reflect to the right side, and the right side is going to reflect to the left side, and so my horizontal asymptote really just stays the same. Remember, the only time you're going to change your horizontal asymptote is if you shift vertically. So I'm going to take each of my black points and reflect it over the y-axis. At -1, 0.37, when I reflect over the y-axis, I get a positive 1, 0.37. At 0, 1, I'm on the y-axis, so when I reflect over the y-axis, I stay put. At 1, 2.72, when I reflect over the y-axis, I'm left at -1, 2.72. And at 2, 7.39, when I reflect over the y-axis, I'm at -2, 0.739. Sketch using your same horizontal asymptote y equals 0, and I have a new transformed function. On my last graph, the purple one, f of x equals 3 times e to the x, notice I still have my same parent function. I'm still using that same black parent function, but this time I'm multiplying by 3, which tells me that my black function is going to be stretched by a factor of 3, and that's a vertical stretch. So all of my y values, or f of x values, are going to be stretched or multiplied by 3. So at negative 1 comma 0.37, I need to be 3 times as tall as 0.37. Well, if you take out your calculator, 0.37 times 3 gets me 1.11. So this point at negative 1 comma 0.37 is going to stretch to 1.1. At 0 comma 1, I'm 1 tall. What's 3 times as tall as 1? Well, 3. At 1 comma 2.72, I am 2.72 tall. Well, 3 times tall as 2.72, I don't know what that is in my head, so I'm going to multiply it. 2.72 times 3 is about 8.16. So at 1, I have a point at 1 comma 8.16. Now I can sketch the graph, and that black function looks like it was stretched in order to make the purple function. Each of my points is now 3 times as tall as it was before. So in summary, we talked about what a exponential function is, with a x variable in the exponent and a constant number in the base, and we graphed using our 3 key points, and we used some transformations, and finally we learned about the number e and used it as the most common or natural base.